So we just talked about particle energy, which brings up the interesting question, can the B field, can the magnetic field change the particle's energy? You would think it probably could. First, let's think back to the E field. I remember a problem just like this a little bit ago. Back in LS2. Let's convince ourselves that it's going to get bounced out. So when the electron is here, it has a charge of what? Minus E. So it's going to feel a force, F equals Q. It's going to feel a force back. Because the field is that way, the charge is negative, it's going to get pushed back. So it's going to have some high velocity, but it's going to slow down, and it's going to get pushed and accelerated back, and it's eventually going to come out. Yes, that is right. That is completely relevant. What we had there was a region where the E field points to the right. And we had this little electron here. And when it flies in, like we just remembered, it flies back out. Flies in with some V naught. It has kinetic energy here. When it flies in, the electric field pushes it back. It goes to potential energy here. And then once it's just sitting there, the electric field shoves it out, pushes it out, and it goes back to kinetic energy there. So we had a particle with kinetic energy, and the electric field pushed on it, converted it all to potential, electrostatic potential, and then converted it back to kinetic. So we did change the particle's energy with the E field. Let's look at a similar situation with the B field. So here we have a region where you have a B field pointing into the board, like that. And it looks kind of similar. Let's have a particle with some velocity fly into the B field. And we've already talked about what's going to happen. It'll follow a circular path and come out with some velocity, with the same velocity, actually. So let's think about what happens to the particle's energy as it goes through here. Well, it's going through uniform circular motion. The force is always perpendicular to the velocity. So actually, the magnitude of the velocity is constant. So basically, you never lose any kinetic energy. Here, it's all kinetic energy. Here, it's the same kinetic energy. You have your kinetic energy here. You have the same kinetic energy there. You never really took away any of the kinetic energy to make potential, to create some potential energy. So this magnetic field isn't actually doing anything to the energy of the particle. All it's doing is turning it and changing its trajectory. Even though we threw the particle in and it bounced out, it went through the whole process without changing its energy. So if we wanted to make a little rule, we could say that the B field does no work on a charged particle. Now, it's always risky to write things in physics because it's almost always proven untrue. So this is too general to be true. Let's fix it in two ways. A static B field. When a magnetic field changes, that's when you do work. We'll get to that later, to induction. A static magnetic field does no work on a free charged particle. If you're just talking about an electron or a proton flying around in empty space, when you apply the B field, they just go in circles. That's all that happens. So then it won't do any work. We can look at the reason mathematically for a minute. Remember that work, if you want to do work, it's the force dotted with the displacement where you move, and that's the reason it's zero, is you're always displacing perpendicular to your force. That dot product is zero. If you want to take the time derivative and see that a little bit differently, you could say that the power that the magnetic field is doing to the particle is F dot V, if you just want to see it in terms of the actual velocity. And we know that the force is always perpendicular to the velocity. So again, the power is zero. It can't do any work. So mathematically, and even in this thought experiment, the magnetic field, the static magnetic field, does not do any work on a free charged particle.